Hey everyone, welcome back to OpenAI Build Hours. I'm Christine, I'm on the startup marketing team, and today I'm here with Erika.
Hi, I'm a solutions engineer at OpenAI.
So today's session is about prompt caching. And this is one of the fastest ways to cut latency and reduce costs. So I'm really excited we're diving deep into this topic today. So quick context on what build hours are all about. It's really to empower you with the best practices, tools, and AI expertise to scale your company using OpenAI's APIs and models. Everything that we're covering today is really designed to be immediately actionable. So you're going to see a lot of live demos as well as a customer spotlight today to show how we actually do this in practice. And if you want to follow along and share this with your team afterwards, you can always find build hours at our homepage, webinar.openai.com/build hours. Okay, so let's jump in and give you a preview of everything we're going to be talking about today. So here is the agenda, and it's really structured to show both the foundation and practical tools to start using prompt caching effectively. So first, we're going to go with prompt caching concepts. So this is going to be 10 minutes. It's going to focus on the foundation, the mechanics behind how caching works, and then a quick API walkthrough to understand what's happening under the hood. And of course, we're going to bring this into practice. Today's live demo is extra fun. It's going to be on an AI styling assistant, but we're really going to show you how to use batch image processing, branching chat, and then long-running compaction in action. And so this is like a real workflow, and whether you're a startup, a developer, you can see how that applies. So then as we're going through this demo, we're really going to show you this like developer playbook, and this shows you the tips on how to maximize cache hit rates and things like the prompt cache key, context engineering, endpoint selection, tool usage, and so on. And then I'm really excited. We have a customer spotlight today on Warp. And this is going to be a real world example, and they'll show you actual impact and metrics on how they've used prompt caching and how that's really changed their workflows. And finally, Q&A. We do have some time for Q&A, but throughout the session, feel free to submit these via the text box so that we can answer them live, and then save a few for answering on air with the last few minutes that we have. So with that, I will turn over to Erika.
Thanks, Christine. Okay, why prompt caching? I will say I love deep diving on prompt caching because in my role as a solutions engineer at OpenAI, there's really three things that I talk about with customers. It's intelligence, latency, and cost. So how can I make things faster, cheaper, smarter? And prompt caching is a way that you can influence your latency and your cost with no negative impact to intelligence. So I think it's kind of a no-brainer as you become more sophisticated in architecting your AI applications to think about prompt caching. So I want to start with an overview, like what is prompt caching, and then talk about how it actually works at OpenAI. So essentially, prompt caching is compute reuse. When multiple requests share the same prefix, we skip fully processing those tokens and only spend compute on what we haven't seen before. And you'll hear me say prefix a lot today. By prefix, I just mean the inputs you've sent us before. So that's like your system prompt, images, audio, messages, etc. That's what we're calling a prefix. So I want to talk about like 101 basics of caching. Essentially, caching starts at 1024 tokens. If you send us a 900 token prompt, we're not caching. So once you send us 1024 tokens, we will start caching in blocks of 128 tokens. And cache hits require a contiguous prefix. And we have to see everything in the exact same order as you sent us before. Like that is the number one key here of caching, is send us the exact same stuff in the exact same order. Eligibility, it's on check completions, it's on responses, and it's multimodal. So we will cache audio, text, images, and it happens automatically. It's what we call implicit prompt caching. You don't have to do anything. There's no changes to your code, and there's no cost. By default, our cache is ephemeral in memory, 5 to 10 minutes, but we have a new extended prompt caching. So you can pass us a parameter and we will store your cache for up to 24 hours. And then there's a ton of optimization, right? These are the basics, but we're going to spend the rest of the build hour talking about how you can maximize for your cache hit rate. And like I said, there's two main things that we care about. Like there's two main impacts of prompt caching. The first is pricing. So when we introduced prompt caching with the 4.0 model family, we gave a 50% discount. With 4.1, a 75% discount. And then with the 5 model family and on, it's 90% discount. I like to throw GPT real-time on here because audio caching on our speech-to-speech model is almost 99% of a discount on cache tokens. So the more you can increase your cache hit rate and have those cached input tokens, the more you can save. This is a huge incentive to focus here. And then the other piece is latency. So this chart, I ran 2,300 prompts, variable length between 1024 and 200,000 tokens. You can see on the left-hand side, there's kind of like a smattering of green and red dots. Time to first tokens, like roughly the same, about a 7% difference for those cached prompts. Whereas if we look on the right-hand side and you can see this sharp increase for the uncached requests, it's like 67% faster for these super long prompts. The longer your input, the bigger impact of caching on time to first token. So you can kind of see that green line is roughly flat because caching keeps latency roughly proportional to the generated output length rather than the total conversation length. Okay, in order to understand the optimizations and the developer tips that we're going to cover, I think it's really important to take just a few minutes to talk about what attention is, what is in this cache, like what is the cache? So attention is the mechanism that lets a model selectively focus on the most relevant parts of the input when processing a token, right? This is kind of like the heart of the transformer model. Attention is all you need. Its purpose is to build the best possible representation of the current token by integrating all the prior context, since that representation is what's driving the next token prediction. And each block, and this is like the most simplified possible version of inference here on the right, but each block contains two main components. There's the self-attention layer and the feed-forward network. That's like the multi-layer perceptron. And in self-attention, tokens are determining what they need to know about the other tokens. In the feed-forward network, each token's representation is going to get refined through linear and nonlinear transformations, but like that's out of scope for prompt caching. We just care about attention today. So as tokens move through these stacked layers, like a model might have 32 or 64 layers, the representations become progressively richer. And this is all parallelized matrix math. Like this is why we need GPUs. To perform self-attention, each token embedding is projected into 3 vectors: a query, a key, and a value. And the query represents the information the token is looking for. Basically, like, what do I need to know about all the previous tokens to contextualize myself best? The key represents what the token contains, like, who am I? What do I represent? Am I a verb? Am I a color? And the value represents the information that it can contribute if it's relevant. And these projections are learned linear transformations parameterized by weights and biases that are optimized during pre-training. And these are specific to each model. And when we think about model parameters, like this is what we're talking about. So the model is computing similarity scores between the query and the key, like how relevant is that previous token? And that way the model can pull in the most relevant signals from earlier words instead of treating all prior words equally. And that's how context disambiguates meaning. For example, when we're thinking about the word river, it's going to shift the internal representation of bank, like riverbank, towards its geographic sense rather than the financial one. And without caching, we're basically redoing all this matrix math that we need all these GPUs for. Like, we don't want to do that. We want to reuse that work that's already been done. And essentially, what's in the cache? It's basically just a giant pile of floating point numbers. Like, we're not storing tokens, we're not storing embeddings. This is what's actually in the cache. So I want to talk about what happens when you actually send OpenAI an API request, because I think this is key to how we're thinking about what optimizations to make. So here's the flow that actually happens when you're making a request to the responses API. So first, we're going to compute and hash the prefix and check that hash in our routers. So what does that actually mean? Like, are we storing the tokens? Are we looking at your first prefix, like that first part of your prefix? No, we're hashing that first 256 tokens, and we're using that and optionally the prompt cache key, which is an optional parameter you can pass us, to actually route to the right machine. We're going to select an engine. So as you might imagine, you can't send 10 or 100,000 requests to be processed on a single GPU. Each engine can only handle about 15 requests per minute. And this is really key when we're thinking about some of these optimizations. We're always going to prioritize engine health. So we will sacrifice some cache hit ratio by distributing traffic. And that's what's really going to get everybody the best time between token for that balanced utilization. Okay, so we've selected our engine. If we've seen your prefix before, we're going to fetch that. And then we're going to look at those future chunks. So we looked at your first 256 tokens, the hash of that. And now we're going to look in those 128 token chunks to see how much have we already seen before. So right, we could have 100,000 tokens in the cache. We're going to keep looking until we see that first mismatched token. Everything after that is going to be considered uncached. So the engine is going to say, okay, what have I seen before? Oh, I see this is my cache hit. Here's my new content. And then it's going to do inference over everything that it hasn't seen yet. So my super high level inference TLDR at the top. We're going to tokenize. We're going to go through embeddings. We're going to go through attention, the MLP blocks, linear projection, softmax, and then we're going to get our predicted next token, which is the whole point here. What's that next token? And then lastly, we're going to update the cache to include the outputs that the model just generated. So the next time you make a request, it has everything you've sent us and everything the model generated in the cache ready for your next request. Okay, awesome. Before we get into developer tips, I want to do a quick demo just to highlight the difference between no cache and cache. So I have an AI styling assistant, this retail tech startup I've just started. One of the things I need to do is process a super high volume of images in bulk. Same prompts over and over again. It's just the images that are going to change. Okay, super small diagram I have here. Essentially, when we're thinking about caching, it's like, what is static? What is dynamic? In this case, what is static is my standard image processing prompt. It's like about 2,000 tokens. And then what's dynamic? It's all the images I'm passing in. I'm going to pop over to this demo I built. There's a lot to look at here, so we're going to walk through it. Essentially, what are we doing? We are analyzing all of my images at scale. We can see my input schema. Essentially, I have the system prompt so that I can pull all the information I need out of my images. And then I have this long response format schema that I'm going to pull back. I'm going to click on run comparison so we can let it run while I'm talking. But essentially, we have three variants here. We've got a cache break scenario where I'm actually preventing caching by inserting a timestamp. And that might sound kind of like arbitrary and obvious, but we've actually had customers who accidentally were including spaces, including dynamic content, including a timestamp, which meant that they're breaking the cache on every single request because the start of your prompt is new on every request. And then the other two things I have here are cache. So I'm allowing implicit caching. I'm not doing anything different, but I have prompt key on or prompt key off. And we're going to get more into this parameter, but what you need to know about this is it's helping us route to the right engine. Okay, great. So looks like we're still running. Let's pull up the cards. Cache break is almost done, but you can see immediately off the bat that including this prompt cache key, like key auto, we can see we have a higher percentage of our cache. So just normal implicit caching, I'm not doing anything, just making requests and not purposely breaking my cache. I've got a 75% input. And then if I have a cache key, I'm getting an 83% input. And then as expected, if I'm breaking the cache by inserting a timestamp, I am at a 0% cache. So we can see just immediately the difference between the cost. We have 35 cents to process these images, just no cache. We've got 22, almost 23 cents for the cached with no key, and then we have 21 cents for the cached with a key. So a huge cost difference between no cache and cache, and honestly, a significant difference at scale between including a prompt cache key and not including it. And as we can see, like my time to first token is roughly the same, because when we're thinking about that latency chart, 2000 tokens is pretty small. So latency isn't the impact here, it's really cost. Okay, let's get into it. We're going to talk about some of the key tips that I have that we've been working with customers on actually enhancing your cache rates. So 5 main things we'll talk about. The prompt cache key, that's super important. Context engineering, what do you need to think about when you're doing context engineering, truncation, summarization, API endpoints, tool use, and then the extended prompt caching parameter. So let's start with prompt cache key. Essentially, this is an optional parameter you can pass into requests. We're always going to cache automatically, like you don't have to do anything, but prompt cache key helps when you have a lot of similar requests. Remember, caching only works if a request shares the same prefix and lands on the same machine. So we're going to hash the first 256 tokens. That's where we're going to identify what engine to land your request on. But if you send thousands of requests with the same prefix, we're going to have to spread those across machines for load balancing. So your cache key hit rate is going to drop. If you pass us a prompt cache key, we're going to hash the prefix plus that key, so you can kind of intentionally group related requests so they route to the same engine. We had a coding customer who started using prompt cache key, and their cache hit rate jumped from 60 to 87%. So a huge increase by starting to leverage prompt cache key. Now, reminder here, we're going to combine it with the prefix hash. And I think this is especially helpful because you might have 256 tokens in common with a lot of requests, but what happens when you have variable content after that initial hash? That's what we're going to look at in this next demo. So when I say branching chat, what am I thinking about here? Well, let's pop back over to Excalibur. Now, I have, as part of my AI styling bot, a live chat so that I can offer support to all of my users. I have a static standard prompt that I'm going to be using. That's just like information about my brand. That's going to be in every single chat request. I'm going to provide that to my customer service agent. But then there's 2 options, right? Users can go into support, they can go into styling. And I have dynamic prompts given where a customer is going. Are they going to support? Are they going into styling? I'm going to have like 5,000 tokens that are different for those 2 flows. But if we're only hashing the first 256 tokens, like those are going to get mashed together. So I'm going to actually only really be getting that 3K in common. So I'm going to pop back into our demo, and I'm going to choose my standard chat here. So what are we simulating? I'm simulating that I have 30 users. They're going into my live chat. 15 of them are going to be going into support. 15 are going to be going into styling. And then we have 5 turns each, like they're, chatting about their order, etc. So I'm going to run the comparison on these, and the variants we have today are cache break, cached with a key, and cached with no key. So I'm adding a key. I've got 2 prompt keys. I've got one for my support and one for my styling. And then cached, right? I'm not breaking my cache, but I'm not doing anything with the key. It's off. And then our cache break scenario tragically continues to have a 0% input, very expensive. So we can see here it's a 31-cent cost for these users to go through. And then we have a difference of 7% by including my cache key. So a 7% increase corresponds from 11 to 9 cents to process this. Again, roughly similar time to first token. These aren't super long prompts, but you can see that if you can think about how your application has branching more than that first hash, branching amounts of dynamic content, how important it's going to be to think about your prompt cache key carefully. And let's get back more into prompt cache keys. There's more than just that initial kind of thought. I want to talk about coding customers because I think this is really important. You're going to have huge code base contexts, tool schemas, instructions, and you might have users asking a ton of questions about the same code base, or maybe you have users that are working across a ton of different code bases. So variable context that you'd be providing to the model. When we're thinking about how you might leverage a prompt cache key in that scenario, there's kind of two options. One might be a per user key. So if you have a reuse across code-based conversations, you might want to think about a per user key, whereas per conversation key scales better if you have users who are in unrelated threads. And like I said, we have a coding customer who increased their cache hit rate by 27% by being intentional about how they were using prompt cache key here. One thing that might be helpful, and if this is not helpful, ignore, but it can be helpful to think about a prompt cache key like a shard key in a database, because fundamentally it's about controlling distribution and locality. Remember, engines can only handle 15 requests per minute. So if you're exceeding a common prefix and prompt cache key, we're going to spill over to new machines. So think about how you're choosing that granularity to maximize, knowing that this is a kind of restriction, kind of like a basic restriction of our inference. But even if that happens, you're just going to get that single cache miss. So every time you go to a new engine, you'll have that first request be uncached, and then subsequent requests will be cached. Again, if you have a coding workflow or other kind of related long context use case, think about how you want to define that prompt cache key. Is it per user? Is it per conversation? Or maybe you want to group users by keys. Like maybe users don't have that super high volume of requests per minute. You want to max out that 15 RPM. So maybe you group users and figure out how you want to bucket kind of like by that grouping. Okay, cool. Context engineering. The longer we get these 24 8-hour running agents, the more important dealing with super long running contexts is. So we want to balance the optimization of the cache and cost against how you're thinking about doing context engineering. Context engineering is fundamentally about dynamically shaping and curating what the model is seeing, whereas prompt caching is really about keeping everything the exact same as what the model has seen before. So this is kind of funny because context engineering and prompt caching are sort of like inherently at odds.
Battery low.
So we want to think about how big of an intelligence boost or a token savings are you getting to make the cache invalidation worthwhile. Okay, context engineering versus cache preservation. Every model has a context window. Maybe it's 400,000 tokens, maybe it's 1 million. Right now, kind of naively, the responses API will either truncate or fail the request based on the parameter you're passing in. So it's either going to just kind of naively cut as many turns, as much context as it needs in order to stay under the context window, or it can just fail. But hitting the context window isn't the only reason that you would want to manage your context. Like fundamentally, the more context you provide to a model, the less accurate it might be. The more tools you provide, the harder it is for the model to choose the right tool. So careful context engineering is really important to keep your agents reliable. And we now actually at OpenAI have 2 new ways to manage compaction. We have server-side compaction, where you can tell us exactly when you want us to automatically summarize, to compact the context that's happened in your session that far. And if you're using Codex, you're probably already familiar with this. We also have a standalone compaction endpoint. So you can make requests to responses/compact, and we'll return back an encrypted compaction. So kind of 2 high-level buckets to think about context engineering. The first is trimming or truncation, which is basically, let's just completely get rid of older turns. And with this, we want to think about how much do you want to drop in order to make that cache invalidation worthwhile? Like how much of that history are we just cutting out? And then the other way is summarization or compaction. So we're not just getting rid of the turns, we're summarizing and providing that as context in the next response. So a little bit more sophisticated. And again, we want to think, how often and how much do we want to compress to make that cache invalidation worthwhile? I think a helpful example here is with the real-time API. Our speech-to-speech model has a really short context window right now. It's 32,000 tokens. Because of that, we really want to be careful about context management. We have this newish parameter, retention ratio, which if you set it, it can make a bigger cut. When you say 0.7 retention ratio, you're basically saying every time we get close to our context window, cut it so that there's 30% gone, retain 70% of the information. So you can think about it this like you're making big cuts less frequently. Because what's the alternative? Essentially, it's cutting every time you're getting close to the context window, which in practice means you're invalidating your cache on every request, right? This is similar to the timestamp thing or adding a space in your prefix. If you're invalidating the cache on every single request, it's going to be really expensive. When we introduce retention ratio, instead of that naive truncation every single turn, you're going to see this like step, you're going to get a bigger cut less frequently. And on 30-minute sessions, you can save 70%. Remember, like, audio tokens are almost 99% off. So this is a huge savings if you can be a little bit more sophisticated with your truncation. I want to show us a demo to think about compaction. Now, the point here in compaction, I'm going to start this, is really to think about not prompt cache key. We're just thinking about the impact of compaction on costs. So this is like a controlled multi-turn staircase benchmark. So each turn is adding a deterministic context. So we can really isolate how compaction thresholds will change the prompt growth over time. So it forces stable model behavior. Like all of these have the same 15 turns, and we're just comparing compaction modes. This is arbitrarily low. Like you're never really going to have a 20K compaction, but you might think about doing context engineering and changing your prompt every 20,000 tokens. So I have that, I have 100,000 tokens, and then I have no compaction. I'm just like letting the model go, letting the cache build. In practice, you probably want a compaction strategy about 80% of your context window. But for demo purposes, let's see what we've got. Okay, compaction off. Maybe let's look at the matrix and drawer here. So compaction off, we can see a total of 245,000 tokens. And that kind of makes sense because we're letting it grow. We're not doing any compacting, and that's 21 cents here. And we can see with a low compaction rate, at 20K, we can see that we have the lowest cache. It's 45%, and that's because we're invalidating the cache more frequently. However, our input tokens are only 82,000 because we're doing this frequent cache. We're not letting our input tokens grow. So it's actually significantly cheaper, even though our cache rate is lower. And then we can see with high compaction, we're not making that many cuts. So we have a pretty similar input as we do for the compaction off, but it's more expensive. So here, it's not that I want to tell you, okay, this is how often you should be compacting or not. It's more consider caching and consider the cost of your input tokens when you're designing how you actually want to architect for compaction, for truncation. So not this is the right way to do it. You know your traffic best. You need to look at your evals to determine where is the intelligence boost worth it to do compaction or to do summarization or to do truncation? And that's really what I want you to think about. Okay, a few more quick tips. API endpoints. Responses API. If you're using reasoning models, the chain of thought tokens that are hidden only get passed if you're using the responses API. Check completions will drop them. And so that's inherently breaking your cache because we're missing those chain of thought tokens. So if you're using a reasoning model, use the responses API. Just switching from chat completions to responses with reasoning models can increase your cache from 40 to 80%. And responses is not just about caching. It passes those reasoning tokens. So there's also a huge intelligence boost. So not only are you getting improvements in latency, improvements of cost because your cache increased, you're also getting improvements in intelligence. So use the responses API, please. Batch API versus flex processing. When we think about our first demo, with this batch image processing use case, if you have these kinds of latency and sensitive workflows, like maybe you're batch processing images every night, you might be using the batch API. fairly new is flex processing. So essentially, you're just passing us a parameter on service tier equals flex. We're going to give you the same discount as you see on the batch API, 50%. But instead of this being an endpoint that you're hitting, this is on a per request basis. So you can control how many requests per minute you're sending us. You can add extended prompt caching, and you can also include a prompt cache key with requests. So you can have way more flexibility about hitting the cache rate that you should be getting with the responses API outside of a batch scenario. So I ran 10,000 requests. I used the batch API. I used flex processing with 24-hour extended cache. Now, flex isn't like a guaranteed SLA on throughput. So having that extended cache really helps. So here you can see I had an 8.5% increase in cache hit rates when I used flex. That's a 23% decrease in my input token cost. So it's not relevant for every single use case, but think about using flex processing or testing flex processing with your kind of asynchronous workloads. 2 more quick tips. Tool use. So when we're thinking about context engineering, providing the right set of tools to a model is really important to make it easier for the model to choose that tool. However, if you change your tools, that's going to invalidate your cache. That's part of what's hashed in your prefix. So we allow you to use this new parameter, allowed tools, that actually lets you specify a curated set of tools on that request for the model without invalidating your cache, right? So tools are injected before developer instructions. So those are part of the prefix, but this allowed tools is not. So you can actually adjust tool access dynamically while preserving your cache hits. And then lastly, extended prompt caching. So this pushes your cache from 5 or 10 minutes to 24 hours. You pass us a parameter, prompt cache retention, 24 hours, and then we will offload your cache from in-memory to GPU local storage, so that this will give you this 24-hour cache. And if you think about a scenario where you really care about that first time to token latency for a long request, you can think about just keeping your cache warm all the time, every day, just sending us a request so that when you have a super time sensitive, maybe user query with a 200,000 token, you're going to get that 70% latency improvement for that request. So leverage extended prompt caching carefully. You know your traffic best. With extended prompt caching, we have seen coding customers save up to 20% on input tokens, a huge benefit. Okay, pricing and latency. We already talked about how pricing discounts have gotten deeper since we've gotten a more efficient inference stack. So we're just passing that on to you. So if you're using older models, think about switching to newer models so that you can leverage that 90% discount on the 5 model family. And if you're using the real-time API, caching is even more important. 2 easy ways to track usage. You can look in our dashboard to see input, cached input and uncached tokens. And then we'll also give you this field in every response so that you can see total tokens, input, cached tokens, and uncached tokens. A call out for ZDR for anybody on the call who cares about zero data retention. We can think about in-memory versus extended prompt caching a little differently because in-memory is ephemeral. It is ZDR eligible. We're not storing anything. However, with extended prompt caching, because we are putting that in GPU local storage, it's not eligible for ZDR because we are actually storing those prompts. I do want to just remind everyone, we're not storing your raw text or images or audio. We're not storing tokens. We're storing the key value tensors that are these like intermediate states. Okay, cache miss checklist. If you just think about these like key reasons that you might be missing your cache and improvements you can make, we've got input content mismatch. So are you changing your tools? Are you changing your prefix? All of these things that might change in that original hash. Has too much time passed? Are you not using extended prompt caching and it's been half an hour? Like you probably won't have a cache. Are you sending too many requests? You're spilling over to other machines. You'll probably see a little bit lower cache rate. Is your prompt under 1,024 tokens? We're not going to cache it. If you're using the batch API with pre-GPT-5 models, it's not eligible for caching. Flex processing is, so just think about that as another reason to try out Flex. Also, chat completions without a reasoning or with a reasoning model, you're going to see a lower cache hit. And a reminder that the theoretical ceiling for your cache hit is always going to be higher than what you're actually going to see in practice. Cache hits aren't guaranteed. Engine health, there's all sorts of reasons you might miss a cache when you technically are eligible for one. And I want to pass it over to Warp and Suraj.
Awesome. Yeah, so thank you so much for explaining all of those concepts and really loved the demo and showing that live. But now I want to welcome Suraj on, who will actually walk through the business plan on Warp. Hey, Suraj, how's it going?
Hey, thanks for the intro, Christine. And awesome presentation, Erika. And hello to everyone tuning in live. I'm Suraj, I'm a technical lead at Warp. Sorry if my voice sounds a little raspy. I woke up feeling a little sick today, so bear with me. Give me a second to share my screen here. Christine, I think you might need to stop sharing. Sweet, thank you. Let me go ahead and share here. Cool. Again, thank you everyone for tuning in. I'm Suraj, I'm one of the technical leads at Warp. For those who aren't familiar with us, Warp is an agentic development environment. In our early years, we started off building a terminal, but today the primary way developers use Warp is by using our agent orchestration platform called Oz. You can launch coding agents locally or in the cloud and orchestrate them together to handle real development work. Today, over 700,000 developers use Warp to do work across the entire development stack. So whether you're just starting to like architect your project, scaffold it, build features on top of it on existing projects, debug issues with existing projects, deploy, monitoring, really Warp helps with all of that. And it works with all the state-of-the-art models and supports all of the standard extensibility primitives that you're used to, like MCP, scales, agents.md, etc. Okay, so why am I here? So my team's job is to make these agents smarter, faster, and more efficient. And today I want to focus on the faster and more efficient part because effective prompt caching is one of the biggest levers we have to achieve that. Cool. So Erika went into a lot of important detail on how prompt caching works once a request lands in OpenAI's backend. And I want to focus on the perspective from those of us who are building on top of OpenAI's API. What can we do to optimize our prompt cache hit rates? So before we even talk about how or why prompt caching matters and how to take advantage of it, it helps to take a look at how a coding agent like Warp actually operates. So agent interactions in Warp naturally form what we call agentic loops, which grow turn by turn. So oftentimes the user will start by giving the agent some sort of task, let's say like in this case, fix compiler error, and then the agent will usually make a tool call, maybe reading some files, maybe running a shell command. The model reasons over that tool output and decides what to do next, and that loop continues until the user's task is complete. And that also means that the prompt is growing incrementally with each turn, which makes our use case very conducive to benefiting from prompt caching. So this is kind of like the context window building up. So you start with your system prompt, your tools, and then you have user query and all the following turns until the model is done. Okay, Erika went over a lot of this already, but just to recap, why does it matter? Why does prompt caching matter? Well, inference can be slow and expensive. These models do a lot of work every time they generate a response. And fortunately, we can use prompt caching to cut down on a lot of repetitive work by caching intermediate computations from previous requests and using these cache values so the model doesn't have to redo the same work over and over. Like you saw in that agent loop, the conversation was growing and the model had already performed inference on proper prefixes. So it would be a lot of redundant and wasted work to redo all of those inference computations. So that's where prompt caching comes in. When used effectively, prompt caching can reduce your cost by up to 90% and improve latency by as much as 80%, which is huge. And at Warp, we get to pass those savings directly onto our users so they can iterate faster and get more done with Warp. So prompt caching is one of the most important tools we have for making agents both faster and efficient. Again, efficiency means less spend for our users. Speed means tighter iteration loops so you can ship more quickly, both of which are really important to serving a great user experience. Okay, cool. So I want to talk about a few different things that we do at Warp to make prompt caching effective. So like Erika talked about, you need to use consistent prefixes, and this is like the #1 rule to making prompt caching effective. Erika talked a lot about these prefixes in terms of tokens, and I'm going to zoom out and talk about, for those of us using the API, what we're familiar with, which are your system prompt instructions, your tool definitions, your user and assistant terms. So what this means is that from turn to turn, you need to render consistent requests to the model and avoid any sort of differences between these turns. So in practice, what this means is having your system prompt be as static as can be. You want to avoid any dynamic content in that system prompt. And similarly, you want your tools to be consistent from request to request. And like Erika talked about, while you might need to change which tools the model can use at a particular point in the lifecycle of the agent, you can use the allowed tools parameter for that. So also importantly, we don't want to invalidate the cache. So once the model has seen some prefix, if you go back and change what the model has seen, you will basically invalidate that cache from then on. So in this example here, I have on the left a request that contained a user query and a bunch of tool call and tool call results after that. But let's say that the user changed their intent of the task, and the way we implemented it naively was to just change the initial user query. Well, that's pretty bad, because that means that every subsequent tool call and tool call result is no longer going to be eligible to be cached until the next time it is cached, which ultimately means more cost and latency for your end users. So instead, what you might consider doing in a case like this is adding a message instead to the end of the trace so far, letting the model know that the user's intent has changed, and that will preserve your prompt cache. Cool. Next slide here. The other thing we do in terms of prompt caching is thinking about our prompt cache in terms of scopes. So at the first layer, we like to think about like global caching. So what that means is we want every request from any user to benefit from some sort of cache on your first request. And what that often means in practice is the system prompt and tools. Because of our volume, we're constantly caching these across the platform. And in practice, this usually means like roughly 15,000 cache tokens on your first request. To make this possible, we remove all dynamic content from the system prompt. Anything user-specific, but still like static or configuration, like let's say your rules or your MCP servers, that's moved into a separate context message that comes after the system prompt and tools, which is the next scope. So at the user level, any given user in Warp is often launching multiple agents in parallel. And oftentimes they're going to have MCP servers, rules, code bases, other parts of their configuration that are going to stay stable across those tasks. And so that means we want to be able to take advantage of prompt caching at the user scope. And to do that, like I said, we insert like an additional context message, which is meant to be like user scope dynamic context that comes right after the system prompt and tools. So that way, if you launch one agent in Warp and then another, you will benefit from prompt caching, from a greater prompt cache hit than just like what you get at the global layer. And then finally, task level caching. So within a single task, the prompt is growing turn by turn. And like you saw for a coding agent, oftentimes there will be many turns, and these will be long traces. And so this is where we get the strongest cache reuse, because most of the prompt remains unchanged between consecutive agent turns. And this is what we optimize for, because for a given task, there are going to be many turns happening in quick succession for a coding agent. There's going to be lots of tool calls, reading files into context, editing files, and so on. So we want to be very efficient at the task scope. And again, for different domains and products, the scopes will look different, and consequently the efficacy of prompt caching, but these are the scopes that we care about. And finally, prompt cache key. So Erika talked a lot about this. The prompt cache key is very, very, very important. Depending on which model provider you're using, caching might be explicit or implicit. When it's explicit, you get to decide what to cache, when to cache it, and for how long. And you get some guarantees about data being in the cache, but it usually costs more. With OpenAI, you get implicit prompt caching, which means that caching is done automatically and you don't have to even think about it. And that means it's also best effort. And so cache hits depend on where your requests get routed. If two requests land on different backends that were like that were part of the same conversation, the cache won't be reused in that case. But luckily, OpenAI provides a mechanism to influence how your requests are routed. so that you can still optimize your prompt cache hit rates. And that's the prompt cache key. When we implemented the prompt cache key effectively, you can see that our cache hit rate more than doubled back in August of last year. We've since made more improvements to prompt caching, but just literally adding a prompt cache key that was task scoped made our prompt cache hit rate much more effective. So that was awesome. And I'll also mention that you should put effort into optimizing that cache key. You want it to be stable enough to maximize reuse, but not so granular that you overflow the cache or fragment it unnecessarily, leading to cache overflow. Cool. I will show a quick demo here. Let me reshare. Give me a second here. Get my warp instance up here. Okay. Sweet. Cool. Okay, so with warp, you can really do anything in the software development lifecycle. In this case, I have a compiler error that I ran into, and I want to get warp to help me fix it. So I'm just going to ask warp here, help me with this compiler error. And I'm using GPT-5.3 codecs here. Let me just, so what you see here is our like internal debugging tool for looking at outbound LLM requests that we make. And so you'll notice that if I scroll all the way down here, we started off with some amount of a prompt cache hit. In this case, it was roughly 2,500 tokens on the first request. But as you kind of see as the conversation progresses here, the prompt cache hit or the number of tokens that are read from the cache increase. So in this case, again, prompt caching is best effort. So often, like, you might not always see it, but if I kind of keep going, you'll notice that as the conversation progresses, we start seeing more and more hits to the prompt cache, like you see here. Cool. And yeah, warp kind of fixed my compiler error for me. I can accept that. Let me reshare again back to the presentation. Okay, cool. So prompt caching is important because you get to save a lot of money and get to pass those savings on to users. So going back to that example I had initially, if we put some simple numbers to it, so let's say we had 10,000 tokens in the system prompt, 5,000 for your tools, and 100 for the user's prompt. Without prompt caching, the user would be spending roughly 2.5 cents for that request. And with prompt caching, we're down to just a fraction of that cost, 1/10 of the cost, so 0.2 of a cent. And that cost compounds. Once you have more and more requests that are building up for a given trace, you're using more tokens, and that will just mean that like you're spending more. And so the costs really compound, and it becomes really important to prompt cache effectively. Cool. And finally, I'll just mention some exceptions. So Erika touched on this a little bit, but using consistent prefixes is not a hard and fast rule. Sometimes you need to edit the context window. There might be situations where you see that a model read in a file that was irrelevant to the user's task, and it's just polluting the context window. So in those cases, you might want to manicure the context window and edit that tool call result out of it, which might break prompt caching, which is going to depend on your use case, and this is something that you need to evaluate. But sometimes that could lead to greater performance and cheaper cost in the long run by just breaking the cache once. Cool. That was mostly everything I wanted to share today. Yeah, I'll just say that prompt caching is something that you need to think about upfront. It really changes the way users interact with your AI applications, especially where cost and latency is really important. Cool. I'll pass it back to you, Christine.
Awesome. Thanks so much for sharing. We do have some really good questions coming in through the chat, and wanted to see if you had some time to join us back on stage and help us answer some of these.
Yeah, for sure. Sorry.
Awesome. Okay. So let's jump back into the slides, Erika, so we can show everyone these questions and then get started. Perfect. Okay. So the first one is for you. It is, what are best practices for applying caching when the system prompt, the first message in the conversation, includes dynamic components?
I mean, I think Suraj covered this, which is essentially, if you have dynamic parts of your prompt, try to put them as far at the end of your prefix, like keep as much static content first. So it sounds like Warp actually puts that in a separate message as opposed to even including that in the system prompt. But I think like anything you can to put dynamic content further toward the end of the prefix that you're sending us, the better.
Cool. Okay, let's go to the next one. This one was a follow-up question. So what message type is used for dynamic context, system, developer assistant, something else?
It sounds like Warp is using like a separate message. And I think this is, I don't know, we're fairly agnostic to that. If you put it at the end of your prefix, like that's fine. If you put it in a new message, that's fine. I'd say like experiment with what works best. And like Suraj said, like your evals will determine where you're getting the best performance from maybe putting it in the prompt, putting it in a message.
Yeah, exactly. We tried a few different things, and ultimately we found from our metrics that the approach we ended up sticking with was the most effective.
Cool. Okay. And let's see our next one. When does prompt caching trigger automatically?
Right. So this is at 1024 tokens. And I think it's really important. I've had customers who want to have really short prefixes, really short prompts, because they're like, well, I'm going to save money from having a 500 or a 900 token prompt. But I was doing some testing. If you increase a 900 token prompt to a 1024 token prompt, you will get cache hits, right? You're never going to get cache hit on a 900 token prompt. So if you start getting cache hits, even if you only have a 50% cache hit, you would save 33% on your token costs by increasing the length of your prompt over that 1024. So you could save a huge amount of money just by increasing your prompt a little bit. And again, this will depend on your evals, but I would say if you're at that kind of far end, close to 1024, but you're under it, like really consider getting to the point where your prompts are going to start getting cached. Let's see what's next. Trade-offs. There's really no trade-offs. That's why prompt caching is so awesome. There's no trade-offs. There's no hit to intelligence. When we think about model parameters, like they're basically deterministic. Those are part of that's like what pre-training is for. And so if you give us an identical prefix, that KV cache is going to be the exact same. So there is no difference in outputs from using a KV cache that is from your previous request to the one that you're doing right now. Like literally the only difference is that we're burning GPUs when we shouldn't have to, but there is literally no intelligence difference, no output difference. There's literally no trade-off for prompt caching. Like when can you say that?
Yeah, we actually saw this question come in a lot during the chat. So I wanted to double click on it because it almost seemed like it's too good to be true.
It's not.
Love that. And then to specify, what about like with real time? Is any trade-offs there?
There is literally never a trade-off. The only trade-off is when you're thinking about how am I architecting to maximize for cache hit versus not, because if you're over maximizing for prompt caching, you might be getting an intelligence hit because you're not doing that kind of context curation. But like literally just caching, no intelligence difference. There is no trade-off. It's only the trade-off in architecture.
Got it. Okay, so one takeaway from this whole build hour, no trade-offs, definitely be prompt caching. Okay, next question here. Are there differences with prompt caching on the completions versus responses API? We saw some activity in the chat asking about completions specifically. So I wanted to double click on that since you did mention the differences there.
So the only difference is if you are using a reasoning model, because reasoning models have hidden chain of thought tokens. right? We're not exposing the full chain of thought. And because that's not persisted, like chat completions is inherently stateless, that's not persisted. And so there's going to be a difference between turns because the model generated these hidden chain of thought tokens and then isn't seeing them on the next request. So that's the reason why there is prompt caching difference, because you're not persisting those. So it's not, if you're not using a reasoning model, it's going to be the exact same. But if you are using a reasoning model, you're going to see lower cache hit rates on chat completions.
Awesome. Okay, so that is our last question, but our next slide is on resources. So if you do have additional questions, feel free to check these out. So the first one is prompt caching doc, where you can find everything that we covered, and then 2 cookbooks. So we have prompt caching 101 and then prompt caching 201, which Erika, wasn't this just published this morning?
It was just published. Let me see if I click into this tab. You can see I just launched prompt caching 201. So we had a 101 from last year, but I included this 201 cookbook. It has a ton of the information we covered today. So you can review this, check it out. It's live in our developer site right now.
So build hours also when we launch things. So definitely look at these links. After this, after we're done going live, I will send all of these emails, all of these resources out in an email. And of course, there's also the code repo. So that will show everything that we've done in past build hours, as well as this one, if you're interested and want to check out the amazing demo that Erika showed during the session. And then I will wrap up with our next build hour. March 24th is all about agent capabilities. Please register via the link, and we will see you next time. Thanks so much for tuning in.